How about now? Ooh. Okay. How about that? How about like that? Is that good? All right. Let's get started. So Professor Franklin was here on Thursday, for which I'm very grateful. I watched him on YouTube. He was awesome. I want to add just one small addendum to the stuff he added to my slides. So he told you a bunch of stuff that was cool in Spark, which is great. I just wanted you to know that that stuff's not unique to Spark. So if you're using other tools, it's also available. So for example, in Postgres, most of this stuff is available. There's a R data frame binding for Postgres, available through open source in Pivotal R. Postgres also has a lot of support for JSON ingest and playing with JSON. And is a viable alternative to things like MongoDB. It has foreign data wrappers for reading and writing external sources. And then you can write user-defined functions in your Postgres code in Python, in R, in Java, etc. And I say this in part because I think sometimes it's confusing to clear what's really new in these sort of big data systems like Spark and MapReduce, and what of those features are also available on the traditional SQL database. So Postgres as a stand-in for a high-function relational database system has most of these features. Microsoft SQL Server would have most of these features. I suspect things like Oracle and IBM would also have most of these features. So if you find yourself using Spark in the field, that's awesome. If you find yourself using relational databases in the field, you can accomplish most of these things as well. You should just mix and match as you see fit. I think any good developer should have a big toolbox and know how to pull different tools out of that toolbox in different settings. So just wanted to make sure you didn't get the sense that that stuff was only available in Spark. Okay, that said, let's pop out of that little slide, which I added to the deck. I did upload Professor Franklin's slides because he cleaned up some of the median stuff in a nice way. And so those slides are available as the lecture notes for today, Professor Franklin's minor modifications to the slides I posted last time. Now, we talked last time about doing some more interesting sort of statistical analytics queries in SQL, and Professor Franklin took you through median about 3 different ways, right? And I think part of the reason to show you multiple ways to do that was, first of all, to emphasize that in SQL, it's a declarative language, so you can say the same thing even just by description in different ways. But also to point out at some level where SQL gets a little crufty, order statistics like median, right? It's called an order statistic because you're asking about the thing that's in order, it's in the middle, right? So things like quantiles are also order statistics. Things like min and max are actually also order statistics. These are things that SQL actually as a set-based language doesn't make particularly pretty. Okay, and it's good to know kind of where these set-oriented languages begin to fall off. They do fall off a little bit in the the naturalness of expressing things like order statistics. So the solution to that in the SQL standard over time was window functions. And Professor Franklin showed you this last time. It's a way of imposing order on relations and then being able to reason about them. And it's done in this very uncomfortable way with these over clauses and these order bys. I don't necessarily expect you for the exams and homeworks to know how to use the window functions in SQL. But I want you to be aware of them because they are much more efficient a lot of times than doing things purely in SQL set-based. So we went over this last time, but I'll repeat it this time. What is this query for the median doing? It's actually taking this table numbers, okay, which has one column X, which contains numbers in it, and it's sorting it once ascending by X. So it's giving you the value X, and for each value X, it's telling you what position it's in, what is its row number if you order it by X ascending, and what's its position if you order it by X descending. So for every value X, we're tagging in what position is it in ascending order, what position is it in descending order. And then if you know it's a position in ascending and descending order, if they're the same, if it's number 10 in ascending order and number 10 in descending order, then it's the median. But it might be off by 1 because there are issues of like odds versus even numbers, right? If there's an even number of rows, then there is no middle value. And so this business at the bottom with the average is actually trying to give you the average of the things that are the 2 numbers in the middle, in case there's 2 numbers in the middle. We actually defined this in previous slides as being min as opposed to average, so you would want to change this to min to be consistent with the previous slides. But what is this query going to do? Rather than those crazy joins or cross products that we saw before, this is simply going to sort the table twice. Once ascending, once descending, assign those numbers. And then, so it's sort of a 2 n log n task. So it's much cheaper than some of those self-joins and things we saw before. All right, so this is actually pretty fast. All right. Anyway, in general, if you need to do things like figure out an order statistic, where's something in order, or suppose you want to do like the 7-day moving average of a stock, which means you need to see the last 7 days of records, that window, the most recent 7 days window, you would do with one of these window functions. And I've left you a link to a tutorial on this. Again, it's not required material, but it's something that'll be useful to you if you're doing analytics in the field with SQL. Okay? All right. Let me give you another set of examples around graphs. And of course, your homework, part 2 of your homework, which is due Thursday night, has to do with graph analytics. So what we're going to do here is we're going to look at a social networks example. Okay, and I know we started this last time. I'm going to review it. Is there a question? Is it due Friday? It's due Friday. Good. So you have an extra day. Awesome. That's good. That makes me feel less late giving you this lecture. That's even better. So here we're going to take a friend graph. Think of a social network. In this case, it's a unidirectional graph, so it's much more like Twitter than it is like Facebook, right? In Facebook, you're either bidirectional or you're not friends. In Twitter, I can follow you, but you don't have to follow me, right? So it's a unidirectional graph, friends, all right, although maybe friends wasn't the best name. And so there's a from, I follow, and a to, you, okay? And then there's a date associated with when I started following you. And then what we're going to do is we're going to create a view, which is the bidirectional version of the friends graph, because actually I'm going to be interested in a bidirectional, or if you like, undirected version of this graph in what we're going to look at next. All right, and I know Professor Franklin went through this last time, 6 degrees of separation, right? 6 degrees of friends. So this is if you wanted to find friend 1, a person who was 6 hops away from another person. All the people you know 6 hops away. So there's me. This is hop 1, 2, 3, 4. This is hop 5. And then if you number the nodes, this is 1, 2, 3, 4, 5, 6. So with 5 edges, you get 6, a person who's sort of 6 away from you. If you like, you can extend this if you prefer to define it more. And all you're going to do to find connections between someone who is yourself and someone who is 5 hops away, or your 6th degree of separation, is to do a 5-way self-join of this both friends table. Okay? So if you did a 2-way self-join, if you just said both friends join both friends, you would find pairs. Sorry, if you did a 1-way version of this, right? If you say select star from both friends, you'd find these 2 are friends, and 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 these 2 are friends. If you did a 2-way join, you'd get this and this, this and this, this and this, right? If you do a 5-way join, you get things 5 ways apart. So this is going to compute all the paths of length 5. Now, to truly find everybody that's within 5, you'd also have to union in all the paths of length 4, and all the paths of length 3, and all the paths of length 2, and then at base, you'd union in just the both friends table, which is all the paths of length just 1, right? Does that make sense? So this is just the 5-hop paths, right? But you also want the 4-hop, 3-hop, 2-hop, and 1-hop paths. All these people are in your orbit. All right, so this is just an example of that 5-hop path. Question?
Would it, like, if it needs to find exactly 5 paths, would it just, like, repeat paths in, like, the middle, and then get all 5 paths?
All right, so it's possible if you have cycles in your graph that you're going to get things that there's paths that are of different lengths to get between the same 2 pairs. So you'll want to remove duplicates in that case. All right, so it's possible that you can get from one source to one destination via more than one path. And what this describes is just paths of length 5. Okay. And if you have cycles in your graph, this will run around those cycles 5 times. Right. It's not particularly intelligent, but it does compute the paths of length 5. Other questions about this? All right, this sort of pathfinding is key to your homework. So if you don't understand this, then you should talk about it with a friend or a TA. I also would encourage you to put in a little example of this schema into Postgres and just populate it. Take a graph, populate this thing. I think your homework comes with some graphs in the tests, right? And just stare at it and try to construct paths of length 2, paths of length 3. Any other questions on constructing paths of different lengths? Yes? Yes? Right. So imagine a graph where, Bob is friends with Alice, and Alice is friends with Fred, and Fred is friends with Bob. So Alice is 1 hop away, but she's also going to be 1, 2, 3, 4 hops away. You'll find her twice at different path lengths. And that seems like a bit of a shame. But the way I've written this, this will find paths of length 5. So it'll find Bob is connected to Fred by a path that goes like this to this. That's 1, 2, 3, 4, 5. And you'll get Bob connected to Fred. So be it. Okay. You can try to make this more efficient. That could be an exercise. You'll need a not in query, right, to find things that you haven't seen before. Other questions? All right, so this is just the basic idea that the way you traverse a graph is through self-joins of the edge table. With that idea, what we can now do is we can go ahead and look at some interesting properties of graphs, social graphs that you might want to know in a social network. So one of the things you want to know in a social network are who are the hubs in the network, who are the influencers, right? Who are people who are valuable to go, say, send messages to or make friends with or market or what have you, right? And so this is interesting to social networks. So one of the metrics that's used for this is what's called the clustering coefficient of a node in the graph. So here's the definition of a clustering coefficient. It's 2 times the size of E sub jk over ki minus 1. What is this? Ki is the number of neighbors of node I. Okay, 1-hop neighbors of node I. Ejk is an edge between 2 of I's neighbors. So if Bob is I, this edge between Alice and Fred would be an EJK. Okay, so this is I, J, K. Okay, so what is this expression? The size of EJK is the number of I's neighbors, the number of Bob's neighbors, who are friends with each other. How many of your neighbors are friends with each other, and how many versus friends of yours who aren't friends with each other? Okay, so we're going to take that and we're going to divide it by, what's ki times ki minus 1? It's a combinatorial thing. Anybody figure out what that is? It's the maximum number of edges between your neighbors. So if you have ki neighbors, each of them could be friends with all the others, right? So the maximum number of neighbors is k times ki minus 1, right? And the 2 on the top is to account for the fact that this is directed, I believe. So the thing at the bottom is an all pairs metric, and the thing at the top is a directed metric. So we're going to double up the top to make it consistent with the bottom and do the division properly, right? So the bottom is all distinct pairs. The top is going to be now 2 times the number of unidirectional edges. Okay, so this is the fraction of your neighbors that are friends with each other. Another way to say that is, are you in the center of a really tightly connected subnetwork? Are all your friends with each other? And if that network is big and everybody's friends with each other, then you're like in the middle of something really awesome, right? Some sort of clique, right? So that's good if you're trying to reach lots of people, because you go to that part of the graph and boom, things propagate really fast. Okay? So that's a metric of the interest of a node. It's called the clustering coefficient of the node. And then in a graph, you can take the average clustering coefficient of all the nodes, and that's the clustering coefficient of the graph. So a well-connected graph, a dense graph, will have a high clustering coefficient overall. Right? And you can ask questions about like subgraphs that have high clustering coefficients, etc. So imagine that you're Facebook and you have, a quarter of the people in the world on your social network. So you've got, 2 billion users or nodes. And you want to know, okay, what's the clustering coefficient of the entire graph? Or maybe you'll do a group by. You'll do what's the clustering coefficient of, people who went to Berkeley versus people who went to Stanford or whatever, right? So you might want to be able to ask this question on pretty big graphs or on pretty big subgraphs. Excuse me. So you want this to scale up, all right? You want this to run on more than one node. So it might be nice to say it in a language that parallelizes, or at least a language that runs out of core. So SQL is such a language. So a very reasonable thing to do is to try to implement the clustering coefficient thing in a language like MapReduce or a language like SQL. All right? And actually implementing in MapReduce is kind of a pain in the butt. So we're going to do it in SQL, which is already pretty weird, but at least you're getting things like aggregation and arithmetic built in kind of a natural way. You may prefer to do this in MapReduce, which is awesome, but you'll go through the same rough thought processes we're going to go through right now. So how do we compute this expression, which is just a simple expression in SQL? Well, all right, let's look at this. We've got, if you like, that picture up above, Bob is at the top. Let me draw it actually exactly the same way here. So this is going to be our directed friend graph. And the picture at the top of the board, we'll have Bob at the top. We'll have Alice over here. And we'll have Fred over here. And we're going to label the edges. We're going to posit that there's a triangle here, because what we're going to want to do is count up triangles. That's essentially what the previous expression is saying, is how many triangles are there in the graph. If two of your friends are friends with each other, then the three of you make a triangle. Right? So we'll call this edge F1. We'll call this edge F2. And we'll call this edge F3. Right? We're going to try to construct triangles and count them up. So here's how this is going to work. First of all, we need to know how many neighbors you actually have, which is ki. That's a pretty easy SQL query, right? We have this relation here already previously, friends, right? So if you are the from ID, you want to know how many distinct to IDs are associated with you. Those are your number of friends. Make sense? So how many distinct to IDs are associated with each from ID? Well, the each from ID thing is going to be the grouping clause, right? Per from ID, I want to know the count of distinct to IDs. All right, and the two IDs, it's because of the key relationships here, or the primary keys here, because from ID to ID is a unique, because these edges are not duplicated in the graph. All we need to know is the number of edges outbound from each node, right? So node ID is the grouping thing, and then the count of things outbound from node ID is the friend count. So that is the ki per node, right? The node ID is the subscript I, and the count is the k. Make sense? Any questions so far? We just computed ki for each I. We good? All right. Now we need to find out how many triangles there are. I know how many neighbors each node has, but I want to know how many triangles there are because I want to do this EJK business. If there's an EJK, that means there's a triangle between me and J and K. All right? Or if you like, Bob, Alice, and Fred. So what are we going to need to do? We're going to need to join together the edge relation. We're going to work with the edge relation. We don't have a node relation anyway. The edge relation, it's going to be F1, F2, and F3. I want to construct this shape every time it appears in the graph. So we're going to have the edge relation once, and we'll call it F1. We're going to have the edge relation a second time, we're going to call it F2. We're going to make sure that F1 and F2 both point to the same guy, Bob. And then we're going to see if there's an F3 between the source of F1 and the source of F2. Make sense? All right, so let's see what this looks like. We're going to take that edge relation, we're going to use it 3 times. So it's a 3-way self-join. But instead of forming chains now, we're going to form triangles. So here's how it looks. F1.toID, that's this end of the arrow. We'll call that root. Okay? F1.fromID, we'll call that friend 1. Alice is friend 1. F2.fromID, we'll call friend 2. Okay? Right? And then it's both friends F1, both friends F2, and then this one, so we don't care actually. Ooh, does this make sense? Sure. I'm not exactly sure. Okay. And then we'll have friends F3. So let's be clear. F1.toID, the endpoint of this edge and the endpoint of this edge are both the same. They're both root, right? And they're equal to each other. Okay. F1.fromID, which is down here, equals F3.fromID. So these are both coming out of friend 1. And F3.toID, the end of this arrow, equals F2.fromID. Then we've constructed this triangle. Make sense? And if you do this for all the possible roots, you will get all the possible triangles, which is what we're doing. Okay? Now, one thing I was staring at as I was looking at this very late last night was, why is F3 friends and not both friends, and is that just a typo? I don't remember, actually. So there's an open question in my mind. Does this query change for some reason if F3 is both friends? I don't think so. I think all both friends does is ensure that if you have a one-way edge, you have a two-way edge. In fact, I think it should be both friends, because we're treating this as a bidirectional or undirected graph. So I'm going to assert that that is a typo and even change it in the slides. All right, so that removes one confusion. Everybody saw how we constructed this graph out of edges, and then we basically repeat it for every possible F1, because F1 spans all of the sources of edges in both friends. I'm sorry, all the destinations of edges in both friends. Okay? So that just found all the triangles. So what do we have now? We have all the triangles, which are IJK triples, such that EJK is non-zero. And we know KI. Okay? So now we just need to put them together, just. So the neighbor edge count, this is the number of, well, actually, I forget what this is. Let's go look at this equal. We've root count star as count from triangles. This is the number of edges adjacent to root that participate in triangles. That is to say that they root count star as count from triangles. So we are taking for each node in the triangles table how many triangles it participates in. Okay, so that's what that is up there. Neighbor edge count is how many of my neighbors per node are triangle neighbors. So that is like EJK for every I. How many of my neighbors are triangle neighbors? They have an edge between them. And now the clustering coefficient per node, we're done. We know EJK. Oh, crap. Excuse me. I think we have to go. Everybody out. Right, and it all uses that hash table from here to build. Right. That could be fun. So we gotta get a prototype like, ANSI. Yep. But that should be just the only thing you have to do there that's weird is this thread pool with the right. But we can use that too. We have to do that. Could you check and see if she's shaping? Are we live? Yeah? Awesome.
Oh, yeah, we're good.
We're good. All right. This is going to be a fun YouTube video. All right, we're almost done with this this crazy clustering coefficient thing. But let's refresh our memories once more. For those of you who stuck around, I hope you enjoyed the sunshine. All right. So remember, the numerator is all of, per node I, it's all of the neighbors jk that are connected in a triangle with I, right? There's an edge between j and k, so they form a triangle with I, per I. And then at the bottom, it's the number of possible triangles that I participates in, okay? And then what we've already computed is that neighbor edge count is the numerator. Well, it's the EJK part of the numerator with the squiggles and the vertical bars. It's the number of triangles each I participates in, okay, group by root. And then we just need to do the denominator, which we already have Ki. We computed it on the previous slide, right? It was neighbor count. So the CC per node is going to be the root, which is the I, okay, so it tells us which I we're talking about, 2 times the neighbor edge count, which is ne.count, divided by n.friend count times n.friend count minus 1, where neighbor edge count ne, from neighbor edge count ne, neighbor count n, when we're talking about the same node, right? ne.root is n.node ID. So for a given node, we look up its statistics in 2 tables. We look up its neighbor edge count, and we look up its neighbor count, and we just can, those are the index I is in the where clause here. And then we're just hooking up the EJK table to the K table. Yeah? So that's it. And then, of course, if you want it for the whole graph, well, that's just the average of the thing we just computed for all the I's. Piece of cake, right? Yeah. Maybe not quite as pretty as it would look in MATLAB, where you have kind of sigmas and summations are a little bit tighter syntax, but not too bad. So SQL is a perfectly fine language for doing things like forming graphs and counting and doing arithmetic and all those things that you need to do analytics and big data. Okay. Do you want to do this in Spark, in Scala, maybe? Scala is actually a nicer syntax than SQL, I think. And because you've got your programming language and your query language kind of better integrated, you can live in that Scala world maybe the whole time through. And that's pretty nice, particularly if you can get the table abstraction into the Scala framework as data frames. But you can do the same thing in Python and NumPy using a database interface and a little bit of magic. So the real reason to look at this is, first of all, if your data does live in the database, okay, then you don't have to pull it out of the database to do this, which is what would happen if you had data frames in the host language. Although not actually in Spark, I think. Spark probably is smart enough to do it lazily. The other thing to note is that if you want stuff to scale up naturally, you need to have some way to express it in a declarative way so that this can be parallelized under the covers by partitioning the edge table automatically for you. So you want a big data framework underneath somehow, either an SQL database or something like Hadoop or Spark under the covers. What you don't want to do is write this in straight line code that thinks that the graph is all in memory and that it enumerates the edges one by one, right? You want to declare this in collections of edges, the way that this is done. Okay? All right. A note for the exam, which is coming up in only a couple weeks. You'll be responsible for all the constructs we mentioned except for window functions and anything having to do with interfacing SQL to your programming language. So all those APIs will not be on exams. In your homework, you can write queries using any Postgres features you like, but don't use the callouts to user-defined code. So you can't go and invoke a Java function, give it the entire graph, and have it solve the problem. That's cheating and also won't scale very well. You really have to stick with the SQL language interfaces. Okay? Okay, with that, we're going to change topics. We're going to shift away from SQL. But before we do that, one more tip. And I've been getting a bunch of questions in office hours, and there's been a bunch of questions in Piazza about performance of queries on Homework 3. And I wanted to highlight both some features in Postgres that will help you understand things, and also make a note about subqueries. So here's our CS186 database, and our favorite tables, boats, reserves, and sailors. Okay, and just to remind ourselves what's in here from the last time we did this, here's the boats table. Here's the sailors table, including Popeye, who we added with the null rating. And here's the reserves table. Cool. All right, so that's the whole database. Now, a lot of people are I think, struggling with the difference between what happens if I use a subquery versus a join. So let's look at something like joining boats and sailors. Select star from boats, natural join sailors, right? Well, that's kind of, not sailors, sorry, reserves. Okay. For each boat, we're looking up the reservations that have the same BID, right? The natural join of boats and reserves. All right. Another way to say this, right? From boats, comma, reserves, where boats.bid equals reserves.bid. Yeah? Okay, you'll get the boat ID twice, but you get the point. All right, this is fine. This is a join. By expressing it as a join, the database system knows to use its favorite join algorithms, like hash join. You can tell in Postgres what join algorithm it's choosing. All right, and the way you do that is before a query, you just add a word, explain. And then instead of running the query, it gives you the query plan. Most databases have these, all right? So it's choosing a hash join. Notice that it's got some kind of estimate of a cost, which we'll talk about when we talk about query optimization. It's also got some estimate of the number of rows at each step of the query, all right? Those estimates are very likely to look completely crazy, like 10,000 rows in this database, until you type this command. What the heck is the command? Analyze. So what this does is it runs over all the tables and it figures out some summary statistics, like how many rows, how many distinct values in each column, what's a value distribution. So make sure you run the analyze command, and then you'll stop getting crazy statistics in your query plans. Okay? But you can look at what this query is doing, and you can see that for these equijoins, it was able to choose a hash join, because after all, it's an equality join. If we look at the one where we say it as a natural join, and we do an explain, still hash join. All right? Now here's another way to write roughly the same query. Select star from boats where boats.bid. Well, let's do this. Boats B, where b.bid in, and select BID from reserves. All right? Let's get the answer to that. Now we're not going to get all the reserve columns out because of the way we expressed it as a subquery. But we do get the reservation, the boats that have been reserved, right? It's a bit different than the previous query, but it's not a great deal different from the following. Oops, I don't want to explain it. I just want to run it. Boats.star, all right? And if we just said distinct boats.star, it would have been exactly the same as the subquery. Why might the join be better than the subquery from a performance perspective? Well, if you don't know the answer, that's okay, because that means you're not a query optimizer, which is fine. I don't expect you to be a query optimizer. You haven't even studied them yet. But you have access to the reasoning of a query optimizer by typing explain. So what happens when we do it as a subquery? Nested loop, that's bad, right? Nested loop join is, as you know, n squared. Hash join is like n log n, right? So why is it nested loop? It's because that in clause, for every tuple in boats, it's running a query on reserves, okay? Or at least it's running a query on reserves and it's scanning through the results for every tuple in boats. Right? And you can see actually this hash aggregate business in the subquery is removing duplicates from the subquery. Okay? So what this is doing is it's a join, all right, where first it's doing a scan of reserves, removing duplicates, and then it's doing a nested loops join of that with boats. All right? The in predicate is going to lead to nested loops behavior because it can't really see the equality join. The join version of this, where you say it as a join, is going to, where'd it go? Here. It's going to see this natural join, or even better, we can make it super explicit, boats B, comma, reserves R. Now you can see it too, where B.bid equals R.bid, right? There's your hashable thing, an equality predicate. Right? So is it possible that, oops, typed it wrong. Isn't that a nice error message? Is it possible that Postgres could figure out these are the same and rewrite the subquery into a join? It is possible. Okay, and I think a more expensive database system might do that for you. But Postgres doesn't, all right? And so probably if your homework's running really slow, a good guess is it's doing a bunch of nested loops joins. And you'll see that if you type explain before your queries. And it's probably doing nested loops joins for one of two reasons. One, because you used a subquery where you could have used a join. Or two, because you forgot to type in the join conditions, and so you just asked for the cross product of two things by accident. That's a possibility. I've seen that in some people's homeworks. Just, you forgot the where clause part that joins up the two tables. So check and see if you're getting nested loops, and if you want to make your queries go faster, that would be a good thing to look for. I see the question. I'll make one more comment. If you get the right answer within, say, a finite amount of time that we can measure before we have to turn back your grades, we'll give you credit. So this homework, you're not supposed to optimize the performance of your queries. Just get them right. But if it's taking you 6 hours to run one of these queries on 500 tuples or something, it's probably because you're doing something crazy. And that might actually be hard for us to grade in finite time. So we do have to assign you a grade in a reasonable amount of time. If it's so slow that we can't grade it, we may have to talk to you. So if you're seeing real performance problems, look into explain and try to avoid nested loops joins. Question?
So the in clause, I might be kind of wrong in how to think about this, but the in clause seems, the with clause seems like it's an in clause, but just run before, or defined before you run the query. If you're describing with view as.
So the question, I think, was how does this relate to with clauses?
Yes.
Okay. So if you say this with, let me see if I can get the syntax right. Select star from reserves. Select BID from reserves as reserve bids. Select star from boats, comma, reserve bids, where boats B, reserve bids are, where B.bid equals R.bid. Like that? There's no subquery here. That with clause is just a macro. It's really just replacing something in the from clause with something in the from clause that's a macro. So it's still join syntax, B.bid equals R.bid in the where clause. This is a plain old, I didn't get the syntax right. No, I'm not exactly sure what I did wrong here. No comma? Oh. Nope, I'm doing something wrong. But I won't debug my syntax right now. The point is this general pattern is still a join. The problem is where you say select star from boats B, where B.bid in reserve bids. Select star from reserve bids. So it has nothing to do with the where, with the with is the point. The with is just a way of kind of encapsulating a bunch of tables and their join predicates. If you use the with table in the from clause, you're getting a join. If you use the with table in a subquery in the where clause, you're getting a subquery. All right, so it's a good question. With is really just a way of bundling up a bunch of stuff. It's how you use it that determines whether it's a join or a subquery. Okay? So it's that subquery in or exists, those kind of things that are causing you trouble. It's when you put queries in the where clause. We good? All right, so that's tip for the day. Explain as your friend. All right, and with that, let's move to a new topic. So we now get into the area of what's called data modeling, or logical design of databases. And it's a thing you got to do. It can be a little dry. It's actually very interesting when you start digging into it. It's super far removed from any implementation details. So one thing in this class, as we talked about, is it spans the gamut from how do you put bits on the disk to how do you model the universe? And we're at the how do you model the universe part of the class. So it's going to be pretty far away from hacking stuff. And maybe you like that, maybe you hate that, but it's, this is a full stack problem, data management. So we're at kind of the top of the stack now. So how do you describe data? Well, you describe it in some data model. What is a data model? It's a collection of concepts for describing data. It's some kind of abstraction, all right? And it's got to be an abstraction we can write down. It's got to be some sort of formalism for modeling information. You're used to this from programming languages. Type systems in programming languages are essentially data models. They're often not well suited to data modeling per se, but it's the idea that I'm going to have a bunch of bits in my computer's memory. How will I think about them? Well, I'll think about them using the Java type system, right? It's an abstraction that you can write down, and it's a formalism. So it's a similar idea here. So a data model is a collection of concepts for describing data. A schema is the description of a particular collection of data using the language of a particular data model. Okay? The relational model of data is the model we'll talk about a fair bit over the next few lectures. It's pretty, and it's simple, and that's why we like it. Okay? Its simplicity is probably its most attractive part. Now, it's old, but that doesn't mean it's necessarily bad. Most things that have followed it have tried to be more complicated or desperately simple. All right? The more complicated things are a horror show for the most part. So things like XML, or if you really try to use JSON as a database, tends to lead you down the garden path. They're very confusing because suddenly things are nested and you're trying to reason about trees rather than tables. And a forest of trees is kind of a hard thing to reason about. The desperately simple alternative is like a key value store where you basically can have a hash table, and that's it, which is a lot like the relational model if I only gave you 2 columns. Right? And one of them was a primary key. So key value things are fine, but they're very, very simple. Most of the sort of semi-structured document-style data models like XML and JSON are actually quite rich and complicated. The relational model is like simple enough that we can do some good with it, and not so complicated that we get confused. So it occupies a nice middle ground. The main concept is there's this notion of a relation or a table with rows and columns. I mean, we've been working with this all semester, right? We sort of know this. But we're going to formalize it and some of its properties over the course of the next lecture or 2 or 3 or maybe more. All right. Every relation has a schema. We know this. It describes the columns, their names, their domains or data types. And we also know from our using SQL that there are these sort of levels of abstraction in the relational model. They're embodied in SQL. There's views which describe how different users see possibly the same data. Okay? So the cow, the puppy, and the baby all have different views of the data. Okay? There's a conceptual schema that defines the logical structure of this data. It doesn't tell you how it's stored. It just tells you kind of what's in it. The views are defined over that. And then below the conceptual schema, there's a physical schema that describes how it's stored on the disk. Okay, what disks is it on? What machines is it on? If it's in a parallel database, how is it partitioned? What indexes are available, and so on. So there's this sort of 3 levels of abstraction. Okay, rather than boats and reserves, the book switches now to courses and students. It's kind of the same thing, right? Replace student with sailor, course with boat, and enrolled with reserved, and you have kind of the same data model. Okay, so fine. But we're going to have some extra things here, so why not? So there's a physical schema for this. So the conceptual schema you see there in a sort of SQL-style syntax. It's got the columns and their domains, names and domains. The physical schema might be, the relations are stored as unordered heap files. There's an index on the first column of students. It's a B tree. They're all on a single disk in my laptop, or maybe they're spread across 700 nodes in EC2, partitioned by name. I don't know, right? Could be anything. That's the physical schema. An external schema or a view might not include the conceptual schema at all. Somebody's view might simply be the course ID and the number of people enrolled, which is an aggregation over the basic conceptual schema. Okay? So the external schema could be quite different. It could be a computation over the conceptual schema. So a key sort of piece of relational database religion is what's called data independence. And the idea, and this goes back to the Turing Award-winning work of Ted Codd in the early 70s, was that applications over databases written before the relational model tended to have all kinds of logic for following pointers on disk. And so you'd be writing a program in an old-fashioned language, and you'd keep following pointers around in this like spaghetti, but the pointers were actually disk axes. And then what would happen is someday you'd want to reorganize the disk, and then all your apps would break or would have to be updated, and that could be really problematic. So the idea was to separate your applications from the way that things were represented on the disk. And this was done at two levels. There was what was called logical data independence, which is to protect you from changes in the logical structure or the conceptual model, and physical data independence that would protect you from changes in the physical structure. So if you like, logical data independence separates the people from the conceptual schema. So the cow doesn't have to care if the conceptual schema changes because you can hide it with a view. So if you decide that, courses and enrolled are going to be one table in the schema instead of two, maybe the cow never sees that at all because he just cares about enrollment numbers. Okay? And then physical data independence separates the conceptual schema from changes in the physical layout. Right? Okay. Why is this notion of data independence so useful in particular for databases? Why are database people more obsessed with this than type system people in a Java programming environment? Well, I'll tell you an anecdote from my mom. Hi, Mom. So my mom was a database application developer back in the bad old days before the relational model, and then in the relational days. And she used to come home at dinner and complain about her colleagues and stuff. And one day she was retired, and she said she got a call from one of her colleagues that one of her applications she'd built for the university was broken. It was like a grade management application, I think, in fact, or maybe it was course registrations. And she's like, well, what's wrong? And they're like, well, we're getting this message. And she said, oh, yeah, I put that in there. That's the message that says that if the code's still running after 20 years, it should just break and someone should have a look at it. That's roughly how the story goes. I forget the details, but that's roughly the story. The moral of the story is, A, my mom's awesome, okay? And B, database applications have a tendency to stick around forever. So the grade reporting applications at Berkeley, I think, are in PeopleSoft, which is a company that was bought by Oracle like 15 years ago. Okay, and these things just don't get updated very often. Why? Because the data they manage sticks around, and it's a drag to kind of upgrade the applications and the data and everything. And so these things tend to have a bunch of gravity. They just kind of stick around for a while, longer than a lot of other applications. And so what happens is the databases evolve faster than the applications do. Right? As the database grows, or as Moore's law moves forward, you have a tendency to move the data around across devices and machines. You build new indexes because you find new uses for the data. Right? But the old apps need to keep running because who really wants to write a new grade reporting app? Right? So it's this weird thing, which I like to call, because databases and their associated applications persist. All right? So this came up in databases because the applications are so long-lived. They're longer lived than the organization of the data and the hardware it runs on. But you can generalize this to lots of domains. So this is what I call Hellerstein's inequality, okay, because I just do. All right? And you figure at some point you got to start naming things after yourself because no one else is going to name them after you. If I was really cool, I'd have a constant. If you can't have a constant, you can have an equality. I'm settling for an inequality, which is actually pretty humble. So the idea is you want data independence when the rate of change of your application is much slower than the rate of change of your environment. If you're running your code on a very volatile environment, if things are changing underneath you very quickly, then you want your application to not have to deal with thinking about all those changes. So a good example of this is writing applications in widely distributed systems or in the cloud. Okay? So in a cloud system where you have elasticity of resources, today you have 10 nodes on EC2, but then you get a surge of usage, and tomorrow you have 1,000 nodes on EC2 because you need it. You don't want to rewrite your code to go from 10 nodes to 1,000 nodes. You want to be isolated from that physical change in your computing infrastructure, right? So you'd like to have that layer of independence, physical independence in that case, between your application code and your environment. Right? So this is not really just a database thing, although very often the reason you scale, or as you scale, your data scales, whether it's more replicated or just bigger. Okay. But this inequality applies not just to databases, but to any place where your application changes slower than your environment. All right. So that's a little background. Get you excited about data independence, not just for grade reports at the university. So data models, let's go back to them. Data models are cool. They connect concepts to like bits on the disk. It's actually a big philosophical deal. All right, this is how we talk about the world in a way that computers can compute on. There are many ways. There are many data models, as I said. We're going to ground ourselves in the relational model because it's clean and common. It's a more generalized version, if you will, of key-value pairs. Key-value pairs are just two-column tables where one column is primary key. This is many-column tables, and you don't have to have a primary key. Okay. And then what we'll use is a kind of visual abstraction of the relational model called the entity relationship model, which is nice at design time. It's actually a formal language, but it's a graphical language. So you're going to draw boxes and arrows and stuff like that rather than write down syntax. But it compiles down to relational directly, and we'll talk about how that works. Why the relational model? I sort of talked about this already. It's very widely used. There are other models. There's old ones like IBM IMS. There's mergers of objects and relations. Some databases like Postgres will provide you with an object model, and then some languages like Ruby on Rails will provide you a mapping from an object model to the database. That's all great, okay? Very useful. We won't cover it in this class, but those are good when you're interfacing your programming language model with your data model. And then, as I said, XML and JSON and similar kind of document models tend to be nested and also semi-structured in the sense that not each document has to have the same structure as each other document. You kind of take the union of all possible tags that anyone ever put in these things, and that's cool. But it makes it very hard to query them if it's very heterogeneous. Okay, there are languages for these models that generalize SQL, essentially. Things like XQuery or XSLT or JSONic. They're like, you look at the XQL part and you go, yeah, I get it, that looks like SQL. And then you look at the rest of it and you kind of go, ooh. And then you put them together, and then you really scratch your head. So I used to have people come in and give lectures on XQuery and stuff who are like big advocates. It's just ugly. All right, so I encourage you to learn it if you need it. I discourage you from learning it if you don't. That's the bottom line. Most relational engines actually have now been sort of upgraded to handle these things. But again, like I wouldn't reach for those features necessarily if you don't need to. It's very nice to have flat objects when you can, flat relations when you can. Okay. So the entity relationship model is the thing that we're going to spend some time on for the rest of today's lecture, which is somewhat limited. So the relational model is a nice formalism. It's clean for building systems, but it's a little detailed at design time. It's a little fussy. It's hard to show to customers and get feedback on. What we'd like is some kind of pictures we can show to people, kind of a graphical abstraction of the relational model. And the entity relationship model works out to be that, okay, although it was invented semi-independently. Before we get into it, let me give you the old-fashioned view, which is still useful sometimes, of how you design a data model. So traditionally, if you're going to build a database at like a big bank, okay, and it's going to store transactions for the bank, and it's going to be, the federal government's going to need reports from this thing at the end of the year to make sure you're in compliance with the FIAA or some FDIC, I don't know, whatever applies to banks. And also, by the way, it's like money, so like it should be right and stuff. So we care about it. Then you'll probably go through a waterfall engineering design process where you'll have milestones. It'll take a year or two to come up with your design, but at the end of it, you'll be like, this thing has been audited 6 ways to Sunday. It's awesome. We can stand behind it. We're going to report it to our stockholders in the federal government. It's all good. If that's your world, and increasingly that's a smaller and smaller fraction of the world, but a very important part of the world, you might go through a process like this. First, you do requirements analysis. You sit down with your users and you say, well, what are you going to do with your data? What information are you storing, and what kinds of things will you need to do with it as you update it and query it? Then you might go through a conceptual design, which is a high-level description of what's in your data. And this is often done with an entity relationship model. And I'll point out that things like Ruby on Rails, object relational models, pretty much are conceptual design. What you do in Ruby on Rails is pretty much design an entity relationship model. And it takes care of a bunch of other stuff for you below that. So it's this thing that people do today very often with like web apps. Okay, so the conceptual design part is kind of what we'll spend time on today. It's very typical even in Agile shops. From there, you do a logical design where you translate the ER into a database model. Now, some tools will do this for you automatically, where they'll automatically take your ER diagram and generate SQL create table statements for you. With Rails, you may need to get a little bit involved in this as well, but it'll do some of this for you automatically. All right, and as I said, we won't cover Rails this year, but some of you may have used it, so I'm populating it into the slides. After the logical design, you actually have to go back and look at the schema and do some refinement. And we'll spend a bunch of time on this. This is where you get your integrity constraints right. And it can be quite tricky. Okay, and so we'll see how this works to get your data truly consistent and normalized. And then finally, you'll do tuning things like physical design, indexes, disk layouts. Last, but certainly not least, you have to do a security design. So what are the views that are exposed to which applications and users over this data? Which of them are read-only, which of them are updatable? If they're updatable views, how does that work? Like, how do you update a view? It's not always a straightforward thing, et cetera, et cetera. So the security design is also super-duper important. So this is all traditional stuff. And we're going to focus today on the conceptual design part, which is common, as I said, even in modern scenarios. So the questions are basic. They're like, well, what are you trying to model in this database? What are your entities? What are the nouns? What are your relationships? What are the verbs at some level? What connects the data? What info about those entities and relationships should be in the database? What integrity constraints or business rules, as the boring business people like to talk about it, what holds there? This entity relationship diagram is going to be a schema, but it's going to be a diagram, which is nice. So our schema, although it's going to be formal, is going to be a picture. And we'll be able to convert it into a relational schema. So this conceptual design is where kind of your software and data engineering begins. Right? And it really is an engineering process. It's an engineered artifact that you want to think through and that traditionally was thought through in a waterfall fashion over long periods of time, very carefully with lots of review. Okay? Now, there's a somewhat different modern usage pattern, which is often called schema on use, which has become quite prevalent, especially in the kind of Hadoop ecosystem. But also you can do it in Postgres and in other relational database contexts as well. You know, you're in a less governed environment. You're not in the part of the bank that's keeping track of the bank accounts. You're in the part of the bank that's like trying to figure out how to sell credit cards to customers. And, you know, every week you run a different ad campaign and it gathers different information from users clicking on the web. Right? Some of them are in magazines and some of them are on the web and some of them are on TV. And they all generate different data. And every time the crazy guys in marketing come up with a new ad campaign, you get essentially a new table or a new log from that ad campaign that you want to integrate into your analytics because you want to figure out how better to target your ads for credit cards. Right? So this is all supposed to happen like every week you get better, right? It's agile. So you're always getting new data, coming up with new analytics, and revamping your ad campaigns to do a better job. Right? You don't have time to do a one-year conceptual design, blah, 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 blah. All right? What you want to do is get the data from those new ads, dump it in a file system as logs, and then let the analysts figure out what information in those logs interests them for their analysis about what they're doing. So you don't let this lack of a schema prevent you from storing data. You don't worry about what are my table names and what are all the columns. You just either dump stuff into a file system, maybe as binary, okay, maybe as text logs. Well, maybe you're lucky it comes out of your software as CSVs or JSONs or Excel files or something, right? It's got some structure. But just put those wherever you can. Maybe you put them in a file system. Maybe you have a database with one column called stuff, and the column, the type of stuff is like, you know, binary. And you have a big table. You want it in the database because it's recoverable and managed and all that, but you don't want to think about modeling it. That's great. That's fine. You can always build views later. Okay? So you just shove it into your database or your file system, and by the way, most database engines can query files anyway. They can't update them. Well, sometimes they can. Postgres can sort of update them. But you know, you can keep it in files if you want, or you can put it in the database. And then what's going to happen is you wrangle this data into shape as needed. Essentially, you're doing the moral equivalent of defining views over this raw data at the time you need the data. So you don't update the data. You just create views or lenses or call them what you will over that data. So essentially, you're doing database design, but you're doing it kind of with views. You actually never store the data in its schematized form. All right? And what do you do about integrity constraints in this environment? It's way too late to worry about integrity constraints after the ad campaign already ran, right? The heck with that. You might want to know if there's weird stuff in your data, though. So you might have anomaly indicators. So instead of saying there shall never be, you know, a user whose age is greater than 100, because it's too late for all that, you say, hey, I'd like to see in the age column if there's any people who seem to be strangely aged. What's the distribution of ages and what are the outliers? Right? So you take a more statistical approach to this rather than an enforcement approach. And similarly, you might do this at a constraint level. So, you know, if things were stored in nested JSON files and you tore them apart with views and put them into separate tables and they don't join back together properly, maybe that's okay. And you just want to flag the things that didn't join back together and say, here appears to be a user without an account number. Sorry, you know, just you might want to look at that. So rather than having constraints, you want to have just detection of anomalies. And those are just queries. Those are just more queries. Statistical queries or looking for constraint queries. And you do them post hoc. This fits really nicely with your data's read-only or append-only. So for log files, this makes a lot of sense. Don't worry about what they look like when they come in. Just worry about what they look like when you query them. It doesn't fit so well with update-heavy data, because as we'll talk about over the next few lectures, if we're doing update-heavy data, we probably want to design it so the updates make sense. Okay. There's pretty good analogies to strong versus loose typing in programming languages. For those of you who've programmed in Java and in JavaScript, or Java and in Python, or Java and in Ruby, it's kind of nice to get away from Java and C and all that strong typing and go to a language where you don't have to worry about writing down the types of all your attributes. And it's great, right? Types of all your data structures. But then, like, you get a month into your code, and it's 1,000 lines of JavaScript, and you sort of get confused. And you really wish you had those even, like, awesome Scala type signatures that really told you everything about everything. That'd be really cool. So, sometimes you want things loose, sometimes you want them strong, and you can do that in data land as well, is the bottom line. All right. Excuse me. All right. So in the 5 minutes that remain, some very simple basics about the entity relationship model. There are entities and there are relationships. Okay, let's start with entities. An entity is like a real-world object, and it's described by a set of attributes. An entity set is a collection of entities that have the same attributes. Okay? So like all the employees might form an entity set. All the entities in this entity set have to have the same attributes in this data model. Okay, so there's no variation in the attribute sets. Each entity set will have a key that describes uniquely which entity is which. So you can distinguish the entities in the entity set by their key attributes. And each attribute will have a domain or data type. And we're going to draw entity sets as boxes, that is to say rectangles, with names on them. And the attributes of the entity set will be drawn as ovals connected by undirected edges to the rectangles. And the key columns will be underlined. So here's an entity set of employees. The key is social security number and nothing else. But there are also attributes for name and parking lot. A relationship is an association among two or more entities. Like Mr. Achu works in the pharmacy department. So the author of the book, Professor Ramakrishnan, spells Achu that way. Perhaps because he's from India, I don't know. But for about the first 10 years I lectured, I thought it was pronounced Mr. Adishu, and I didn't get the joke at all. So he cleared that up for me. It's Mr. Achu. So I don't know if that's an American thing. But anyway, he works in the pharmacy department. Relationships can have their own attributes. Like, for instance, how long has he worked in the pharmacy department? That's an attribute of the relationship between Mr. Achu and the pharmacy department. So a relationship set is a collection of similar relationships. Any n-ary, that is to say, relationship that connects n entity sets, any n-ary relationship set relates n entity sets, E1 through En. Each relationship involves individual entities from those entity sets. So here's the employees entity set. Here's the department's entity set, which has a key department ID. And here, drawn as a diamond, is the relationship set works in. Okay? And this way of connecting diamonds to rectangles is how you talk about which entity sets are in this relationship set. All right, and entity sets can have attributes too. All right, so in this little visual language, you can connect up rectangles with diamonds. Both rectangles and diamonds can have ovals hanging off of them. All right, you're not allowed to connect rectangles directly to rectangles, and you're not allowed to connect diamonds to diamonds. All right, entities are related through relationships. Relationships connect entities. Okay, and I think that's probably all we will do today. So I will see you on Thursday.